Alright, here's an introduction to rotational kinematics. And what we need to do first here is talk about some different angular quantities. First things first, the angle theta, we can figure that out. That's theta is equal to the arc length L divided by the radius R. Now, that is important to know that theta is in radians. And remember, what you need to look at is that there are 360 degrees in a circle, and we know 360 degrees is equal to 2 pi radians. Now, just for a general point of reference, we'll be measuring things in radians quite frequently, and 1 radian is equal to approximately 57.3 degrees. So nothing new, nothing monumental there. A lot of our measurements are going to be taken in radians. Alright, so our next thing we're going to look at here is angular velocity. So velocity is a very common term we use in physics, obviously. If you remember just the basic definition of velocity, velocity is equal to the change in displacement over time. So as we write that, and that's just simply delta x over delta t. So that was when we were talking translational motion. Well, now we're talking rotational, so that's a position around a circle. So angular velocity is the symbol omega here that kind of looks like a curly W, and that would be the change in angle theta over the change in time. So nothing terribly different in that we were looking at change in position over change in time. Now we're simply just looking at the change in angle over the change in time. And then for instantaneous angular velocity, hopefully you remember our calculus tie-ins, we'd have angular velocity omega is equal to the limit as delta t approaches 0 of change in theta over change in time, or simply d theta over dt. So just like we've done before, where we talked dx dt being velocity or instantaneous velocity, d theta dt is the instantaneous angular velocity. Alright, so next we want to look at angular acceleration. And, well, acceleration is the rate at which velocity is changing, so no big surprise here. That's going to be change in velocity over change in time. So we have another new symbol here. That's actually an alpha. And alpha kind of looks like an A, so that's helpful. We have alpha is equal to, of course, the change in angular velocity over the change in time. So once again, we like to do our little calculus tie-ins. So we'd have angular acceleration alpha, and that's not a great drawing of that. You may want to look that up somewhere else, but that's of course equal to the limit as delta t approaches 0. We would have change in velocity over change in time, which is just simply equal to dw, or omega, over dt. So we're talking instantaneous rates of change, so we're doing derivatives just like we've done before. Alright, so if you remember on our AP equation sheet, we have 3 main kinematics equations for linear motion. Well, we have 3 main equations for rotational kinematics. They're actually pretty much exactly the same, except we're going to put rotational variables in there instead of the linear ones. So if you remember, we had our linear equations And the first one was v velocity is equal to initial velocity plus acceleration times time. We also had the v squared equation. V squared is equal to VO squared plus 2a delta x. And then last but not least, we had that position equation for an accelerating object. X is equal to x initial plus initial velocity times time plus 1/2 at squared. So in rotational, everything looks exactly the same, except we're going to put our new equations in there. So here's rotational. So first, instead of v, we have our omega, rotational velocity, is equal to initial rotational velocity plus rotational acceleration, alpha, times time. We then have our rotational velocity squared is equal to the initial velocity squared plus 2a delta theta, and that a is actually an alpha there, showing that rotational acceleration. And last but not least, remember whenever we're talking in terms of position for angular, we're talking in terms of theta. So we have theta equals initial theta plus omega initial t plus 1/2 acceleration alpha t squared. Alright, last but not least, we want to show the relationship between our linear kinematics, what we're used to, and our new rotational kinematics here. So, we have an equation here that describes the displacement of an object moving in a circle. That's just simply S, where S stands for the displacement is equal to r theta. So what we want to do is then take a look at rotational velocity. So what we're going to do is take the ds over dt, the derivative of the position with respect to time, and set that equal to r times d theta over dt. And remember, change in position, or the derivative of a position time graph, gives us velocity, and that's going to be equal to, still the radius, that's a constant there, times d theta dt, then becomes omega, rotational velocity. And then for rotational acceleration here, it's going to look very similar. What we're going to do is take the derivative of the velocity with respect to time. So we have dv dt is equal to r d omega over dt, which then becomes acceleration is equal to the radius times alpha, the angular acceleration. So there's a basic introduction to some of our new equations here. What you'll see in the next pencast is some of those equations put to practice.